When we started this unit in lesson 1, we started by looking at variation, and we did that because inverse variation gives us an example of what we call the reciprocal functions. So the reciprocal function is a function in the form y equals 1 over x, where you have x in the denominator. And we've already seen that creates a basic graph that has one branch in the first quadrant and a second branch in the third quadrant. As I'm sure you can imagine from our study in previous units, we're not always locked into the first and the third quadrants. In fact, if we were to reflect across the y-axis, or reflect across the x-axis, we would end up with graphs in the second and fourth quadrants as well. And what you'll also see is we can get a little fancier as we move through this unit. We can add powers onto the x, and that will actually change the relationship of the branches. Instead of being sort of in opposing quadrants like this, they could both be in the upper two quadrants or both be in the lower two quadrants, but getting a little bit ahead of ourselves. You heard me use the word branch. The branch refers to just one of each of these two pieces of the graph. I believe this is the first time you've seen a graph that's not just in one piece, except a little brief look at step functions. That'll come up later. So this is the first time that we've got a graph with more than one branch. There's a summary here that I took straight from your textbook. It's called the reciprocal function family, and we're going to notice a few things. We can have stretches and compresses to reciprocal functions. You'll see those when one changes to some other number. So it's described as a stretch if we take the absolute value of a and that's a number greater than 1. It's considered a shrink or a compression. We don't usually use the word shrink. We usually use the word compression. That would be more consistent with what we've talked about in the rest of this year. And that shrink happens when you have an a value that's between 0 and 1, so a fraction or decimal between 0 and 1. And then if a becomes negative, like with all the other functions we've studied this year, we're going to take and reflect across the x-axis. And of course, all of the functions in the reciprocal function family, we don't allow the denominator to be 0 because then that wouldn't be defined. We can't divide by 0. The other thing you're going to see with this family, in addition to being able to stretch or compress and being able to reflect across the y-axis, is of course we can translate in the same ways that we've translated in previous units. So if I add or subtract something to the x itself, that's going to shift us left and right. And if we add or subtract something essentially to the y value, then that's going to shift things up and down. All right, so let's take a look at how to put these ideas to work. In number 1, we're asked what is the graph of y equals 4 over x, where x is not allowed to equal 0. So we're supposed to graph, and then we have to come up with things like x-intercepts and asymptotes and all that fun stuff. So this is similar to the problem that we did on a previous note sheet when we had y equals 16 over x. I mentioned that there's no little thing that you can memorize like there is with say a quadratic, your 0, 1, 2, 3, 0, 1, 4, 9. Here we simply need to use the fact that we know that we're going to have a branch that goes this way and a branch that goes that way, because that's the shape of a reciprocal function, so that we can guess some positive values and use those to come up with the negative values. So when I choose my x's, I can see that they're going to have to divide into 4. So I want to pick numbers that sort of play nice with 4. So if I divide 4 by 4, I get 1. And if I divided 4 by 2, I would get 2. And if I divided 4 by 1, I would get 4. I do also maybe want to look at a fraction or two. If I divide 4 by 1/2, remember dividing by a number is the same as multiplying by the reciprocal. So if I were to say y equals 4 over 1/2, that's like 4 times 2, which we know to be 8. So there's my value. And that's going to be kind of helpful in seeing what happens close to the axis. So I can see that there aren't any translations on this particular one, because notice there's no minus h or plus k going on here. So I can go ahead and put my axes right in the middle of the screen. And unlike the one from the previous note sheet where we really needed to change that scale, I can fit numbers like 4 on here without changing my scale. I don't want to go to the hassle of changing the scale if I don't have to. So let's graph the point 2, 2, the point 1, 4, and the point 4, 1. I can see if I got all the way out to 8, I'd be down at a half. And I'm sure you can imagine if I only went over a half, I'd be all the way up at 8. So I know I'm going to get off the grid before I get to the next lines. So it's going to look something like this. And that first branch is going to get some labels. We've got 1, 4, 2, 2, and 4, 1. But remember, there are 2 branches to this graph. We only plugged in numbers for the first branch. We can figure out the other branch. We would have -2, -2, -4, -1, and -1, -4. And the branch would be the same shape. Oh, I sort of missed that middle point. Let me try that again. There we go. And just as we've done in previous graphs, we're going to go ahead and label. It can get a little tight to get all the labels in here. Just do the best you can. All right, so now we're asked to go a little bit further. It says identify the x and y intercepts and also to state the asymptotes. Well, we mentioned this the other day. There are always 2 asymptotes with a graph like this. Remember, an asymptote is a line that the graph approaches but never actually touches. And in this case, it's the x and y axes. Well, if the asymptotes are the x-axis and the y-axis, then we can't have any x and y intercepts because we're never going to meet those axes. So it's almost a trick question. Then we're also asked to state the domain and range of the function. Well, once you've determined the asymptotes of a function, stating the domain and range is just not that difficult because the asymptotes will point you in the right direction. So x can be anything except for 0 because we skip over the y-axis, the place where x is 0. So x is not equal to 0. And then the range is also everything except 0. Y cannot equal 0 because we skip over the x-axis as we go up and down. For example, it goes up forever, it goes down forever, but it approaches the x-axis in the middle. It never gets there, so it never has a y value of 0. So that answers the other part of the question.